Hi, everybody. How are you guys doing? Does anybody have questions from homeworks or anything? We had a turn-in here on Sunday, if you forgot to do that. But does anybody have questions from that? About what to do or how to do stuff? Okie dokie. All right, well then let's just dive into the new stuff. So today we're going to look at 13.3. And to start here, we're going to start by getting in our time machine. And we're going to go back to, say, like 6th grade or so. And we're going to ask you to do a problem like this. 2,359 divided by 26. To do this kind of a problem, how would you do this? Yeah, long division, right? Not calculator. So to do this, you start by looking, okay, how many times does 26 go into 2? Well, none. Into 23, okay, well, none. Into 235, well, that's probably what, like 9 times? So 9 times 26, that's 180 plus 54, so that's 234. Oops. And you kind of subtract down. You have 19. So 0 times this 26 go into 19. And you have like remainder 19, right? So you'd say the answer to this problem is 90 plus 19 26ths. Bless you. That was a lot of them. So just a little bit of vocab for the parts of this problem. So the 2,359 is called the dividend. The 26 is the divisor. The answer to that is the quotient. The leftover part is the remainder, and we write that as a fraction over the divisor. So you could say this is like, that division problem is 90 and remainder 19, or you could say 90 and 19 26ths, if you want to write as a mixed number. Does that all look familiar? As something you remember doing from, I don't know, back in like middle school-ish times? So we're going to extend this idea today and do this long division not with numbers, but instead rather with polynomials. So let's say we have the polynomial 2x cubed minus 4x squared plus 5x plus 1 divided by the polynomial x squared minus 3. Remember that a fraction bar is the same thing as division, right? So far, so good. So we'll set this up the same way. We're going to have the divisor on the outside, and the dividend goes underneath. Now, does anybody notice something you might want to do differently for this problem than the setup that we currently have? Take a look at this guy. What do you notice about this polynomial? Yeah, it doesn't have a spot for the x's, right? We go from x squareds to constants, but there's not a spot for the x's. So what we're going to do, we want to make sure we include that spot. So I'm just going to put like a 0x spot there. And that's just going to make sure that everything lines up nicely when we go to add and subtract things later on. Is it recoverable if you don't include something like that? Sure, but it's really easy to make a silly mistake like adding an x to an x squared or something because things aren't lining up the way you expected them to. So I always suggest checking to see if you're missing any spots and putting those 0 terms in there just in case. Okay, we ready to go? So what we're going to do is we're going to ask what times x squared gives us 2x cubed. 2x. So we're going to write a 2x above. And then we're going to multiply that 2x by the entire divisor and write the answer underneath. And because we've included that 0x term, when we do that, everything lines up nice for us, right? The x squareds are under the x squareds, or the x cubes are under the x cubes. Yes? Oh, thank you. Yep. Great. Arithmetic, guys. Okay. So one of the most common places students make a mistake when doing this process is in this next step where we do the subtraction. The place where students make their mistake is they don't distribute the negative sign through. So I always like to do that. So I'm going to erase my parenthesis and push that negative sign through. So everything that was positive became negative, and everything that was negative became positive. So now it's just going to be like adding down. So 2x cubed plus 2x cubed, well, that's 0. Negative 4x squared minus 0x squared, well, that's still negative 4x squared. 5x plus 6x is 11x. And then I'm going to just kind of bring that plus 1 down. And I'm going to repeat and say what times x squared gives me negative 4x squared. So what times x squared gives me negative 4x squared? Negative 4. And again, I'll multiply that to the entire divisor and write that down below. And then subtract down. And again, place where common mistakes get made. Hi, Edie. Thanks, dude. Ava, here it is. Is not distributing that negative through, so I'm going to go ahead and distribute that negative through. So all the minuses are going to become pluses, and all the pluses are going to become minuses. And then I'm just going to add down. So my remainder then is going to be that 11x minus 11. So the way I'll write my final answer is I'll have dividend over divisor is going to equal quotient plus remainder over divisor. So far, so good. Do you remember doing this last year in Algebra 2? You should have done this in an ideal world. So this process is nice, and it can actually tell us a lot of stuff. But what we're going to start building towards today is maybe a more streamlined version of this process. So we're going to start first by looking at, okay, a pretty nice theorem says that, hey, if I have some polynomial f of x and I divide it by some other polynomial x minus k, that's a polynomial whose leading coefficient is 1 and whose degree is 1. We call those types of polynomials monic polynomials. If that's the case, then the remainder is just going to be f of k. That I could just plug in k into the function and I'll get the remainder to come out. So for example, if I have f of x equals 2x squared minus 5x plus 4, and I want f of 2, well, we could just do our old standby and plug 2 in. If we do that, we have 8 minus 10 plus 4. So that's just going to be 2. Or we could think about it as a division problem. Where I want to find the or what multiplies, or what times x gives me 2x squared. Well, that's 2x. Multiply that by the divisor. Subtract down, -1, multiply that through, that's negative x plus 2, subtract down, and I get remainder 2. So the takeaway is that either way is going to give us the same value, right? So I could use division to do substitution. I can use substitution to find my remainder, right? Now, of all the possible remainders, or all the possible numbers you could get for remainder, which number is the most important remainder? Of all the possible numbers you could get as a remainder, which number is the most important remainder? 0. Great, exactly right. Why is remainder 0 important? Because it implies then the divisor is a factor of the dividend. So for example, if I take 6 and I divide it by 2, I get 3 remainder 0. What that tells me then is that quotient, 3, times the divisor, 2, is going to equal the dividend, which is 6. It allows me to factor that number. So if we combine that observation with the remainder theorem that we just looked at, we can make what we call the factor theorem, which simply says that if I have some polynomial f of x with a then it has a factor x minus k if and only if f of k is equal to 0. All right, let's say we wanted to show that x plus 3 is a factor of 6x cubed plus 25x squared plus 16x minus 15. If I look at this as x minus k, that tells me the k needs to be negative 3, right? Because x minus a negative 3 is x plus 3. Is everybody okay there? So I could do just f of negative 3. It's negative 162 plus 225 minus 48 minus 15, which is equal to 0. And since I have that equals 0, it implies that I have a remainder of 0, so x plus 3 is a factor. Or I could do this using long division. So 6x squared times x is 6x cubed. And I subtract down. And then 7x times x gives me 7x squared. Then I subtract down. And then negative 5 times x gives me negative 5x. And I subtract down, and I get remainder 0 again. So either way we're doing it is telling us the same thing, right? Which way seemed easier, the red or the blue? The red stuff, right? The red seemed way simpler, didn't it? Well, here's the catch, though. Since x plus 3 is a factor of 6x cubed plus 25x plus 16x minus 15, we can write that polynomial as x plus 3 times something, right? Here's the catch. The blue tells us what that something's going to be. The red does not. So ideally what we'd like is to find a process that's as quick as the red, but still gives us that extra piece that the blue is giving us, right? That's what we want. Does that make sense to you guys, what we're trying to search for? It turns out there's another way to do these polynomial division that will accomplish this. It is synthetic division. What's the one catch with synthetic division? Well, it doesn't work all the time. You do need to do that, but it only works sometimes. It only works if the divisor is a monic polynomial, like an x plus k. So if we went back and we looked at that very first problem where we started, where my divisor is degree 2, you cannot do synthetic division with this problem. It is only a long division problem because the divisor, not a monic polynomial. So that's the one catch with synthetic division. But for the most part, with what we're planning on doing with synthetic division, it is going to work just fine. So let's kind of show you what to do here. So let's take this same problem that we did using substitution and then using long division, and then do this as a synthetic division problem and show you how this is going to give us a result quick like substitution did, and still give us the other factor like the long division did, which is really pretty sweet. So we want to start by setting the divisor equal to 0. And solve that. So I get -3. Next thing we do is set it up. So my setup looks like this. I draw a little division bar. That the solution to the divisor set equal to 0 goes there. And then the coefficients for my dividend are going to go here. Yes. When you're doing that, when you're writing the coefficients in, though, you have to be careful. We have to remember that those missing terms need to get zeros there, right? We need to put a 0 if there's a missing term. Now, there weren't any in this particular problem, but I'm going to put a note there in this example because that's a place where if you did the long division, if you're paying attention, it's recoverable if you don't put the 0 there. Here, unrecoverable, right? You will just not get the right answer. So to do the synthetic division, the first step is we just bring this first number down. And then we're going to do divisor times this number below. Write the answer in the next open spot and then add down. And then I'm just going to keep repeating that process until I'm out of spots. Yes, sure. So these numbers at the bottom now have a meaning. We want to read these numbers from right to left. This first number is the remainder. The next spot is the constant term. The next one is the coefficient for the linear term. So that's like the x coefficient. The next one is going to be the coefficient for the quadratic term, like the x squared term. And so on and so forth. We just keep going up 1 degree as you move one number to the left. So what we can say is that this is like the best of both worlds, right? We're getting the remainder and we get the quotient. So what we can say, again, is that the solution to this division problem, let's write it this way. Right? And since the remainder is 0, if I multiply both sides by x plus 3, what I'm left with is a partial factorization of that polynomial. You guys okay with what we've done here? So this is actually really important because this actually fills in some of the areas for our solving tree or solving flowchart from last time where we couldn't do anything more. So if I go back and I grab that solving guy, where are you? There you are. Zoom out enough so I can see it. Just grab that and bring you over. Oh, oh boy. Oh boy. Okay. So you notice that if I had something with 3 terms that wasn't in the quadratic form, there's nothing I can do. This process now allows me to possibly continue that. Or if I had 4 terms, but I couldn't do it by grouping, this allows me the possibility of continuing. Or if I have 5 or more terms, this now gives me the prospect of being able to continue. So this, what we've just kind of outlined, this idea of, well, maybe I can just do like one of these synthetic divisions to find a factorization, allows me to fill in more of this factoring tree and allow me to factor polynomials that I wasn't able to do before. Here's the catch, though. Or here's the problem for us. Okay, great, Mr. Kulik. That's awesome. I love that for us. I'm really excited. But in this example you gave me, you knew x plus 3 was going to be a factor. If I don't know what that's going to be, like, am I just blindly guessing because, Mr. Kulik, there's like infinitely many things you could write, x plus 1, x plus 2, x plus 3, x plus 4. Is there like some way to weed that down so I don't have just like infinitely many like needle in a haystack blind guessing? There's things you can do without even needing your calculator to weed this down from infinitely many to finitely many. Yeah, that's where we're heading. That's great. So one thing that we can do to weed this down a little bit is use what's called the rational zeros theorem or the rational roots theorem. And it says that if I have some standard form polynomial, the possible rational zeros are always going to be of the form P over Q, where P are the possible factors of the constant term, and Q are the possible factors of the leading coefficient. So that's really nice, as it's going to allow us now to create a list of possible factors to check. And this is what my pre-calculus experience resembled when I was in school, because we did not have graphing calculators. This is how we did this type of a problem. So we would have started by identifying it's the constant term, which is -4. What are my factors of -4? 1, 2, 4. You're missing 3 more. The negatives. And my leading coefficient is 3. What are the factors of 3? Yeah, plus or minus 1 and 3. So my possible rational zeros, my PQ list, are going to be all the factors of the constant term divided by all the factors of the leading coefficient. So I'd have 1 over 1, negative 1 over 1, 2 over 1, negative 2 over 1, 4 over 1, negative 4 over 1, 1 over 3, negative 1 over 3, 2 over 3, negative 2 over 3, 4 over 3, and negative 4 over 3. So I'd have been left with 12 possibilities here that I would have to check, which is a lot better than infinitely many. Now, super annoying to write out this, especially if there's going to be like maybe 20 or 30 or 50 of these things. Let's agree on a simpler way of writing this. So what we'll do is we'll say, okay, I'm going to say that that's the same thing as just me writing this. And we're just going to all agree that those mean the same thing. And you could write it either way. Everybody's cool with that, I hope. Especially if there's like 20 or 30 or 40 or who knows how many of these possibilities. Like, ay caramba, I don't want to write them all out. So far, so good? Okay. Now, this is still not great as I'm left with 12 things still to check, right? Now, again, when I was a student and we didn't have a graphing calculator to really narrow this down, there was another theorem that we would use that would help us possibly eliminate more than one of these at a time. So we might also have used this theorem. This says if f of x is a polynomial with a leading coefficient, and we divide by k using synthetic division, if that k was positive and every number in the bottom line is non-negative, that is positive or 0, then k is an upper bound for all of the real zeros of f. So, for example, if I had the following list that we just made, and say I checked 1, and I saw the synthetic division at the bottom, that bottom row of numbers was all non-negative, it would tell me that 1 is an upper bound for all of my zeros. So I could eliminate 2 and 4 and 4/3 without actually having to check them. Because if that's bigger than all the zeros, anything bigger than 1 I can throw out also. So it allowed me to get rid of more than 1 at a time. Now, did that always happen? No. Every time I did a synthetic division, was not able to eliminate more than 1 at a time. But when it did, that was nice. And then similarly, it works if k is a negative value and that bottom row alternates between negative and positive. It would allow me to call that a lower bound. So for example, if I was doing that with -1 and I got the bottom row alternating between positive and negative, non-negative and non-positive, it would allow me to throw out all the things that are less than -1, like -2, -4, -4/3, without having to check those. So again, was very useful to me, pre-graphing calculator. Less useful to you when you do have a graphing calculator, but still helpful in doing the following kind of problem. So let's look at an example here real quick of a problem that you just have, that this theorem is what you'd use to do. So it says, show that every real zero of the polynomial f of x equals yada, 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 lies within the interval -5, 4. So I'm going to start with the lower bound on that interval. So I'm going to just do my synthetic division. So I'm getting that alternating. And I would do the same thing with the positive 4. So this is really the kind of problem that you'd need to use this upper bound, lower bound theorem to do, is just to show something as an upper bound or lower bound, which is much easier than just be like, look, the other way you could do it is you could find all the real zeros for this polynomial and show that -5 is smaller than all of them and positive 4 is bigger than all of them, but that seems like a lot more work than just doing this. Okay. So let's kind of put this together and we'll show you the way we'd really want to approach this. So let's say we wanted to find all the real zeros for the polynomial 6x cubed plus 23x squared minus 83x minus 30. I'm going to start by making my PQ list. So my constant term is -30. So my factors are 1, 2, 3, 5, 6, 10, 15, 30. And my leading coefficient is 6, so my factors are 1, 2, 3, 6. Ay caramba, that's going to be a long list if I wanted to write that all out, right? But again, we agreed we weren't going to write out, enumerate every possibility. We're just going to write it in this kind of compacted form. And now what I'm going to do is I'm going to look on my graphing calculator. So I'm going to start just by going to the y equals menu and typing in my function that I'm looking to find the real zeros for. So I'm just typed it in exactly like it looks like on my sheet of paper. I just graphed this on the standard window, so if you needed to reset your window, you just do like zoom standard. I already did that earlier, so my window is back to normal after doing all the scatter plots from last chapter. So if I look at this, I remember that x-intercepts and zeros are kind of the same thing. How many x-intercepts do I see from my graph? 1, 2, 3. And I remember from last section that the degree of the polynomial is, our polynomial have at most that number of zeros. You remember that? So our polynomial is degree 3, so we should be seeing at most 3 zeros. If I can see all 3 of them, I know I found absolutely every possible one of them. So I know this is everything that I need to be looking for. If I look at those x-intercepts, it looks like this one, if I count my tick marks, 1, 2, 3, 4, 5, this looks like -6. And then something in between -1 and 0, and then something in between 2 and 3. Is everybody okay with that? So the things that could be in between -1 and 0, well, let's think here. You could have -1/2, -1/3, -1/6, -2/3. Well, -2/6 is the same as -1/3, so I won't bother with that. I could have -5/6. And then in between 2 and 3, well, let's see, I could have 5/2 and 10/6 is too big, 15/6. And I might be the only 2 in there, right? So these ones still are up in the air, right? But this one seems like the only choice. Does everybody feel okay with why I'm going to choose what I'm going to choose? In addition, if I have my option, would you rather do synthetic division with a whole number or a fraction? The whole number, right? Like, goodness gracious, don't make me do arithmetic with fractions if I don't have to. Right? If I have the choice, like, give me the no fractions, please, and thank you. The other thing I want to point out that I'm also going to look at, as long as I have the graph, is remember we had this multiplicity definition from before, where if we look at how the x-intercepts are occurring on the graph, it tells us about the multiplicity. So specifically, I'm going to look at to see, do I have any bounces or bends? So if I go back and I look at my calculator again, that looks like it's going straight through, as does that one, as does that one. So I think these are all straights. So they should only be used one time, but I'm going to make note of that. That's also something I would definitely be checking. Now that I have this, I'm going to go ahead and choose that -6 and start my synthetic division. Does everybody feel good so far? So what this is going to tell me then is that this polynomial that we started with factors to, since -6 gave us a remainder 0, x minus a -6, or just x plus 6, times (6x squared minus 13x minus 5). Is everybody okay with how I've gotten to here? So what I would do next is, this piece is not monic, right? That's a degree 2 polynomial. Perhaps that could factor some more. So I could attempt to either do a synthetic division, guessing at one of these values, or, since this is quadratic, I could default to my factoring flowchart and simply factor that as a quadratic. That's what I'm going to choose to do, because that sounds more appealing to me than doing a synthetic division with a fraction, especially when I'm not sure even which one of the fractions I'd be wanting to use. Does everybody feel okay still? So to factor this, I'm going to look for the two things that multiply to give me 6 times -5, and then add to give me -13. So what multiplies to give me -30, and then also adds to give me -13? So my suggestion to you is to start always with the multiplication problem. And just, if you're not sure, make a list. So like 1 and -30. There you go. So if you go ahead and just kind of start cranking through the options, it usually reveals itself relatively quickly. Now remember, that doesn't tell you how to factor this immediately, since the leading coefficient is 1. But what it does do is tell you how to break that middle term into -15x plus 2x, so that we can factor by grouping. So from the first group, we can take out a greatest common factor of 3x. Oops. And from the second factor, we can take out a, stupid, it's a 5 there. A nothing, right? So I'll just put a 1 there. If I look at the first, or the two terms now, the 2x minus 5 is in common to both of them. So I have this. So that allows me to say that this polynomial now factors completely 2x plus 6 times 2x minus 5 times 3x plus 1. And if I set this equal to 0, I get my solutions as -1 or -6, 5/2, and then -1/3 by setting each factor equal to 0. Does that feel okay? Look familiar? You probably spent a fair bit of time last year doing this process in your Algebra 2 class. That's enough, I think, for today, because that was a whole heap of stuff. at this point, you guys should be able to do up through 35. And I would try to be kind of up to date on your homeworks, because next class, that might be important, that you're up to date on homeworks. Just saying. Because what might happen? Yeah, that might be something that happens. Be a good reason to be up to date on your homeworks.
Is it next class?
I mean,
oh wait, we don't have school.
You're already counting it off.
Literally like 3 teachers are telling me that.
I know. I'm just saying.
I know a lot of teachers are like, we're gonna plan for math Thursday, then I do the test in psych on Thursday, and the teacher is defeated because he has to figure out when to take that.
Yeah. I don't have any tests this week. All my tests were last week. Which now I feel really good about that I did that.